8, yes, the one that we did yesterday. And thereafter, we're going to start doing our revision. We're just going to do a summary of everything that was done um, in this chapter from last week, Monday, when we started chapter 5, from stoichiometrics, whatever. We're just going to go do a revision on it, which means that tomorrow we're going to be doing the problems. How I structured this, I structured it in a way that today we're just going to go through all the theoretical thing that we've been doing with stoichiometrics and everything in chemical change, part 1. And thereafter, we're going to do homework, but I'll be able to explain to you guys which problems you guys can do, so that tomorrow we're just going to be going through all those problems. So tomorrow it's just going to be problems that we are going to be dealing with. I hope that everybody is having a great time and you guys have done your homework. Okay, let me just quickly go to the textbook and just see the homework that I had you guys do yesterday. I know it was a bit, rough because it wanted some theory, etc. But I tried to do some of it. And okay, let's see. Okay, so for the part, because yesterday, if you guys remember properly, we started the part of explosions. We did explosions, and I asked you guys to go do number 3 and number 4, but I asked you to do number 4.1 because with the expanding gases. Okay, so what it says here, it says the engine of a car uses expanding gases that forms this chemical reaction. Okay, so what they wanted us to do here, they wanted us to do some research and write a short paragraph of this reaction, of what is this reaction and what is it for. So they asked us to also have some chemical equations. So what I did for you guys, I just did a quick summary, because these are stuff that you guys can get into an exam and you can be asked, because it's a type of a reaction that you guys should know. Okay, so I did a quick rough sketch of a of a summary, and I hope that it's going to make sense, but I'll be able to go through with it with you guys. Okay, so what do we know first? I'm sorry, I've got a left hand right hand handwriting, so I hope you guys don't get confused. So basically, what is this? This is a combustion reaction. That's the first thing that we know about it. So what does that mean? It means a combustion is a high temperature exothermic, which is heat releasing, is what we spoke about yesterday. Redox, which is oxygen adding chemical reaction between a fuel and an oxidant. Okay, usually atmospheric oxygen that produces oxidized, often gaseous products in a mixture termed as smoke. Okay, let me explain this to you. What I mean here, I mean that, okay, when you have a combustion reaction, number one, um, whatever reaction that you have, there's going to be oxygen that's added to it. Okay, number two, the reaction is between a fuel and an oxidant. Okay, that's what I meant. A fuel, which is the CH that will be given, plus your oxygen. Okay, and this is in atmospheric oxygen. Okay, not artificial or anything. It's just there. Okay. Number two, what do you know about this? A combustion reaction always has a hydrocarbon. Okay, like in this case, it's our fuel that they're talking to us about. Our fuel, which is I think here it's C8H18. Okay, and a product formed is always carbon dioxide and H2O. That's another thing that you guys can write. So these are points that are explaining why the reaction is like that. Okay, so the fuel you burn in your car engine contains octane, which is the C8H8 that they gave us there. Combustion cannot take place without oxygen. So what have they given us? This is a C plus oxygen, which will give us carbon dioxide and H2O. So I don't know if you guys understand this problem. Basically, we were just deciphering what kind of a reaction it is, what it means, and how do we get our result. I don't know if you guys understand, but if you don't, just hit me up with a chat and tell me, and I'll quickly explain where you get lost. But we're going to get to more to redox reactions when we start next week with chapter 7, and that will give us some more insight of combustion reactions, redox reactions, etc. So don't be too confused with this one, because here we're strictly talking about explosions. Okay, so going back to the question that we are doing here. On number 4, they say when ammonium nitrate is heated, it undergoes a thermal decomposition reaction represented by the following formula. Okay, this is our formula. So they say here, if 500 grams of ammonium nitrate is heated, calculate the total volume of gas produced at STP. Okay, this one, I totally like this question, and I did the first one because the total volume is a problem that we haven't dealt with here in this chapter so far. We haven't dealt with the total volume of the gas produced. So that's why this one was quite interesting for me, and for us to do. I hope that everybody got it right and actually did the problem. um let me quickly just go there. Okay, so this is what you have. This is the equation that you have. um And then what we do first, because what we're given is the ammonium nitrate, which is this one here. What we do, like we always do, we first take the given and we convert it to number of moles so that we can be able to calculate what is required of us. Okay, so we're going to say the M, which is going to give us this, the molar mass, and from there we calculate the number of moles, which is going to give us 6.2467 moles. Okay, and after that, this is the equation that we're going to use. Remember, our N over ratio is equals to N over ratio, unknown ratio, and the number of moles ratio. Okay, so in this case, what we're going to do, we're going to have the N, which is the given one, the NH4NO3, ammonium nitrate, divided by the ratio. Remember, guys, what the ratio is. The ratio is the number that is here, which in this case is a 1. Okay, and that all will be equals to the N of gas, because you can see here they just ask us the total gas. So there's 3 gases here, so which means that we're looking for the number of moles of this entire 1, 2, 3. So how are we going to do that? We're going to come to this ratio of gas here, and we're going to say it's 2 plus 4 plus 1. Okay, do you guys understand me? Are we together? I hope that we are. And if you're not, just drop me a chat. We're going to take these number of moles here of all 3 of these gases, and then we're going to say it's going to be a 7. So which means here we're going to have 6.2467 divided by 1 is equals to N gas divided by 7. Okay, this is new. We've never done a problem like this before, but you guys need to know it. Okay, and then from there, this is what we get. I'm so sorry for the untidiness. I was just trying to work it out so quickly, and I lost some track of time, so I couldn't write it over. But I hope you guys understand what I mean here, because I tried to write it here times 7 divided by 1, and then this will give us 43.726 mole of gas. So this is the gas that we're given. Okay, and then thereafter we're going to say VSTP, the volume at STP, is equals to Vm times N, and that will give us 978.88, or in this case they run it off and it gave them 980 dm cubed. Guys, are we together? Did you guys manage to do this one? Okay, because we've got a lot of things to do now, I'm just quickly going to go back and finish off the work that we did yesterday. Okay, let me just get it here. Okay, yes. Okay, we're moving to our part 2 of yesterday's work, which was part of the gaseous reactions. So now we're going to go straight to the chemistry of airbags. I don't know if you guys have heard it before. Chemistry of airbags. Okay, so what do we know about this? Okay, when there is a collision, Na3 is triggered. What does this mean? In an airbag, for an airbag to react during an accident, there's certain steps that need to be taken. Okay, so number one, there should be a sensor that triggers the electric circuit um, when the collision takes place. And this, guys, it's so fast that you don't see how it started. So it happens in like 4 seconds. So the N2 gas needs to fill up quickly in the airbag and quickly come out and make sure that you fall on it, because it prevents you from falling onto the windscreen and having an accident. And that's what the airbag does. But slowly the airbag starts deflating too, to ensure that the person is not suffocated. So about this, there is a certain reaction that takes place during an airbag. Let me just go to the slide quickly. Okay, yeah. So there are 6 main parts of an airbag system: an accelerometer, a circuit, a heating element, explosive charge, and the bag itself. Okay, so the accelerometer keeps track of how quick the speed of your vehicle is changing. So which means that it's always working, it's always in motion. Okay, so when your car hits another car or a wall or a telephone pole, etc., the accelerometer is what is triggered. So the circuit then sends an electrical current through the heating element, which is kind of like the ones in your toaster, except it heats up a whole lot quicker than a toaster because the accident happens so fast. Okay, so this ignites the charge, often solid pellets of sodium azonide, which is the NaN3, which explodes. So this is the gas that we have in the airbag. Okay, the explosion produces nitrogen gas that fills the deflated nylon airbag packed in your steering column, dashboard, or car, and at about 200 miles per hour. So you can imagine how quick that reaction is. So parts of the airbag, okay, we're not going to talk about that. The most important part was the chemistry of the airbag. So I hope you guys now know how an airbag operates. And okay, here it is. Here is the typical reaction of an airbag. And I know this is not new to you guys, because this is the exact reaction that we had in one of our problems. Plus carbon gives us this. So as the reaction takes place, the gases that form move rapidly. But what also is important, and why we're doing it here in chemistry, is because there's 3 reactions that take place during, oh sorry, I'm in the wrong place. The physics of an airbag, I'm so sorry. uh, yes, here. So with the gas, with the airbags, there's 3 reactions. We've got the initial reaction, which is triggered by the sensor, which is this one that I spoke about. Remember, I told you guys that there's a trigger that happens because there's an electrical circuit that's always tracking how fast your car is moving. And then the second reaction is this one, which is the Na plus KNO3, which gives you the K2O plus Na2O plus N2. And then we've got the final reaction, which is the K2O plus the Na2O plus SiO, and that is alkaline silicate. So what happens, even when the airbag deflates, it has to go on a slow motion to make sure that you do not get harmed, because it can't just blow up and then deflates immediately. So this is also a process. So I just wanted to finish that part about the airbags. So nonetheless, we can move on and go to our summary of the chapter that we have. If you guys remember properly, we started this chapter very early last week, and we were doing psychometric concepts. Okay, psychometric concept, we know number one is a branch of chemistry that deals with quantitative relationship between reactants and product. What does this mean? It means that if you've got A plus B, which gives you C and D, here in stoichiometric, we want to know the quantity, how much of A, how much of B, how much of C, and how much of D. So we want to know how much your reactants using and how much did they give you at the end. So that's the stoichiometry. So that's the branch of that chemistry that deals with the quantities between reactants and product. Okay, a mole of a particle indicates a certain number of particles. Okay, that one we've learned. It is the quantity of matter that contains the same number of elementary particles as there are carbon atoms. Okay, this is the one. Remember this part. This is what we dealt with in the beginning. And we know that when they ask for the number of particles, you take whatever number of moles and you multiply it by the Avogadro number, which is this one, and you will get your number of particles. Okay. So the formula mass or the molecular mass, this is also what we also dealt with, I think, in Unit 3, is the sum of the atomic masses of all atoms in molecules of a substance. Okay, so 1 mole of a particle has a mass equal to the molar mass. The unit is m, and thus G per mole minus 1. Okay, so I hope that you guys remember all of that, because this is a theory part. So molar concentration is a concentration of a solution and is the amount of solid in moles dissolved in every 1 dm cubed of solution, which is N is equals to M over M. You guys know this one. This is our first step every time we calculate. This is our second step after we balance the equation. So number one, we balance the equation in our problems. Number two, we convert the mass into the number of moles, and this is the equation that we use right here. And when we use this equation, you guys do remember, this is the mass, will be given. You always take what's given, and the molar mass is what you need to calculate. Another thing I wanted to remind you guys, do not forget, between elements you add them, but when there's a subnumeral, you times whatever subnumeral with the element that is in front of it. Okay, so don't forget that. Don't multiply the things together. This is not maths, it is physical sciences. Okay, so gravimetric analysis is used to determine the percentage of a substance made by which element. I hope you guys remember the percentage yield that we also did, whereby they want to know how much of this, for example, when we're doing an experiment, this was where we were doing experiments, and there's a theoretical and there's an actual. So what do you want? We want the molar mass of the element in the compound. So if a compound, for example, if we have Fe plus I plus S gives you FeS, we want to know how much of the Fe is there in FeS, and that is what we calculated here, the percentage yield. Okay, if you guys remember that. And then we had the empirical formula, which is the simplest formula of a substance. The true or molecular formula is a multiple of the simplest ratio. And then we did the Avogadro's law of volumes of gases that state that equal volumes of gases at the same pressure and temperature contains equal number of molecules. What is this? This is the STP. This is when they ask you to calculate any gas at STP. And we know one thing about the STP. With the STP, the volume is always 22.4. And when do we use it? We use it after we get the number of moles um, of the unknown, and then they want the volume at STP. So volume M will be volume at STP will be the number of moles times the volume, the molar volume, which is 22.4. And that is what you use whenever they want volume at STP. you know that you need to find the number of moles of unknown, and then you multiply it by 22.4. Are we still together, guys? This is just a quick summary of all the work that we've done. And another thing that I want to remind you guys is that we are working here from the Oxford Successful Textbook, and you can get it from Snaplified. You guys can download the app, and you can download the app, and you can register yourself, and you can get yourself all your textbooks, not just for physical sciences but for all your subjects. And that can help you, because here in this program, in the African Teen Geeks Physical Sciences grade 11, we are using the Oxford Successful Textbook. Why do we use this one? Because it's much easier when you're following from a certain textbook than using random ones. We can only check with other textbook when for example, I'm presenting, or we need some other problems that we'd like to work with. And guys, if you guys have problems, so far I'm explaining the stoichiometric concepts. If so far from the stuff that we've spoken about, there is something that you are battling with, please guys, let me know so that I can go back and explain it to you thoroughly so that you guys can understand it. Okay. So, 1 mole of any gas at STP will have a volume of 22.4 dm cubed, and this is the molar volume. Okay, do not forget that, because it will always be asked. They'll always want volume at STP, and you guys must know what to do. So, a stoichiometric calculation uses mass ratios. What does that mean? Or volume ratios, to determine the amount of product made or reactants needed for a chemical reaction. This takes us back to our ratios. Remember the one where you say N N1 divided by ratio 1 is equals to N2 divided by ratio 2. So we know that N1 is the number, is the moles of what was given, and N2 is the unknown. So N1 is the known, N2 is the unknown. So that's how we find our unknown, by using that equation. I hope that makes sense to you guys. If it doesn't, let me know, and I'll go to a quick example to show you guys how it's done. Okay, so that was it. So then we move to the experimental yield. I don't know if you guys remember, with the experimental yield, this is where you have okay, for example, we are going to do an experiment. So in our experiment, what they tell us is what they want. For example, they tell us the product that they want us to make 15 centimeter cubed of substance X, and they give us the amount of volume that it must be, but they don't tell us the mass of what they want. So what do we do in this case? Um, we need to calculate. We need to do pre-calculations before the actual physical experiment, because the physical experiment, we also need to know how much we need to yield. So when an experiment takes place, number one, you're going to have pre-calculations. These are calculations that you do, for example, to know the amount of mass that you're going to have to measure your solid, and you're also going to need to know how much you'll actually get after the experiment. So that is why pre-calculations are there, and that is why they're done. Number two, your experiment will take place according to what you calculated on your pre-calculations. Number three, after that, now you need to compare if you got the exact amount, because our theoretical yield is 100%. There is no percentage error because it's calculations. But in actual fact, when you are doing an experiment, what is going to happen? You might lose some of the powder or substance that you're using because of air. And remember, there's also impurities in the air, or the plate that you're using, the petri dish that you're using, it might have some problems there that affect the result of your experiment. So when we do the percentage yield, we want to know how close you were from having a perfect experiment. It will never be 100%. There is no experiment that comes out 100%. There's always a percentage that is yield. So it's always better when you have about 90% or 95% yield, and the 5% is lost due to impurities or loss of substances, or in or anything can happen. No matter how perfect you do experiment, it won't be 100%, and that's how something that you guys need to know. And I hope that you understand that part. Okay, then we move to the reacting solutions. Oh, this one was a beautiful part that we did. This one, we talk about volumetric analysis is used to find the concentration or volume of a substance. So what is this one? This is the part where we did the standard solutions. In a standard solution, we know one thing. Okay, we know a couple of things. The first thing, when you're doing a standard solution, you need to have your solute, which is what you got, which is something that can be measured in grams, something that has mass. Okay, and then number two, you need to have a liquid. It could be water or distilled water or pure water. Number three, you need to have your volumetric flask. Our standard solutions are done in a volumetric flask. Okay, and then when we do that experiment, um, when we do the experiment, we add the things together and we close the volume using a funnel. You pour your solutions, and then you close the volumetric flask, you shake it, and thereafter you find your standard solution. I hope you guys understand. That's how you get your standard solution. So usually in a solution like that, there is a limiting reagent. A limiting reagent in a standard solution is a reactant that will completely be used up. Remember what I said to you guys. For example, when you're about to bake a cake, if 4 cups of flour will give you 10 kg, 10 liters of cakes. But if you have two, that means you can only get half of it. As much as all the other things are there, you've got your eggs, you've got your water that you can use, or milk. But this one, flour is your limiting reagent, because you cannot do more than what your flour can produce. So that is our limiting reagent. Is the one that when it's completed, the reaction cannot continue to go further. So X plus B in limiting reagents, when we look for the limiting reagent, what they will give us, they will give us two masses, which is for both reactants. So what we're going to do, we're going to look for the limiting reagent by equating them and finding a ratio. And how we're going to do that, we're going to take the number of moles, which is the ratios, the ones that are in front of the number. We're going to divide them by each other, and then after that, we take the number of moles of each of them again, and then we divide it by each other. What we get from that, that is going to give us, we're going to know that if for example, we have N1 divided by N2, and then we're going to calculate first our number of moles ratio. Let's say the moles ratio is going to be 1, the one that we use, which is the number in front of your element or compound. If that one gives us 1, it means that when we calculate the number, when we divide the number of moles and say N1 divided by N2, the answer that we get there, if it is more than the one that we got, it means that our N1 is our limiting reagent. But if it's more than the 1, it means that N2 is our limiting reagent. I hope that you guys understand what I mean. And if you don't, please let me know, because this is our summary and we need to make sure and wrap it up and make sure that everybody understands what we're doing. So that's the difference. Let me try and see if I can't get an image of yesterday's homework, just to show you guys what I mean by what I mean by the limiting reagent. Because I think with the other ones, with the other calculations, we've been doing them so many times, but with the limiting reagent, it was something that we did close to the end, so we haven't revised it much like the other ones. Okay, so let me just show you guys an example from one of the problems that we did. Okay, this is the limiting reagents. Okay, for example, they're giving you Fe and they're giving you S, and they say all of this is equals to FeS. Okay, so what are they going to give you? They're going to give you the mass of Fe and they're going to give you the mass of S. In this case, we do not know what is the limiting reagent. What are we going to do? First, we're going to calculate the number of moles of Fe and then calculate the number of moles of S. Thereafter, okay, we'll have our number of moles for each. Then this is the ratio that I was talking about, that NFE divided by NS. You're going to take the number that's in front of your element, which is 1, divided by 1, and this will give us a 1. So now this becomes our baseline for calculating the number of moles and knowing which one is going to be our limiting reagent. So this is like the neutral point. Okay, so thereafter we come back again, we take the number of moles, we're going to take Fe and divide it with S, and this is going to give us this answer. So what do we know? We know that if this if this ratio, if you calculate this ratio and it gives you a number less than 1, then our limiting reagent will be Fe. But if we do this ratio and we get a number that is more than 1, then our limiting reagent will be Ns. And guys, why do we need a limiting reagent? We need to find the limiting reagent because that is what we're going to use to look for our product. So that's the most important part, because you can't just use anything for your product. You need to get your limiting reagent. And in this case, you see, we found the limiting reagent and we use that as ratios for the product to know how much of the product we're going to get. So that's the importance of looking for the limiting reagent. And I hope that you guys understand that part. Okay, let me just go back. Okay, so the limiting reagent is a reactant that will completely be used up. It determines, you see, it determines the maximum amount of product that can be produced. The other reactants will be in excess, so it doesn't matter because there'll always be more. But like you've seen in the previous days, we've also had problems where we had to calculate the reactants in excess. But I'm sure we're going to have some more of those problems when we do our revision and extension problems tomorrow. Okay, so it says many reactions produce gaseous products at high temperature. We use rapidly expanding gases for a variety of purposes. We can break up large rock cups in mines, inflate airbags in a vehicle, or move a pistol in an internal combustion energy. So I think you guys you've seen when we were doing the gaseous reactions, these are certain reactions that are dangerous, but they are done because they are done because they are done in a chemical reaction way. So chemistry is big and it's also done in industry. So those are some of the things that you guys have to understand, is that the chemical reactions that we have can be explosions, especially explosions. These are combustion reactions, exothermic reactions that happen whereby energy is released, and they released energy and heat. And these are some of the things that we were doing here. So if you guys have any problems, especially with understanding the gaseous reactions, because we didn't spend a lot of time there, please guys drop me a chat and let me know. But nonetheless, tomorrow we are moving on to revision and extension. Okay, I was just trying to think. Maybe for the maybe for the stoichiometric calculation with composition and substance of molar mass. I'm just trying to think if we should do odd numbers or do even numbers. I'm thinking for the theory part, because this is a theory part, we can do oh sorry, I'm just trying to move on to the next page. Guys, we're officially closing down chapter 5, and please guys, do these problems. Let us work through them, and you know, um yeah, I think there's another page. I think that maybe we should do the let's do the odd numbers for the theory and do even numbers for the calculations. You guys with me? Let's do the odd numbers for for the first theory, because that is going to be theory questions. And then for our calculation, which starts here, stoichiometric calculations, concentration, limiting reagents, and percentage yield. This part, we're going to do the even number. So we're going to start from number 2 and do 4, 6, 8, 10. So tomorrow, we are strictly doing calculations, nothing else. And plus the theory part, this side, we're going to do the odd numbers, which means we're going to do 1, we're going to do 3, 5 gram is dissolved into calculate. Oh, it's also calculations. Oh, I thought this part is theory and this is calculation. But either way, for this first part, we're going to do odd numbers. And for this second part, let's do the even numbers. Guys, please let us do these homeworks. These homeworks are going to help us because it's just practice. And also, you guys can bring questions. If you guys have questions that you have in this chapter that we're doing currently, and you want to find out, maybe you can bring them here, send me a chat, and we can go through them and see how much we can do to help you understand the problem. So guys, let us work together. Let's do these problems. I'll have the problems tomorrow, and we'll go through them one by one until we are done, and we're dusting off chapter 5. And on Monday, we're going to be starting with chapter 7, which is continuation of chemical changes. I think it's part 2 of chemical changes. Let me just check it. But we are on a roll. We are concluding chemistry very soon, and then after that we'll go back and start doing electricity. But for now, this is where we at. And guys, please do your problems. I hope that everybody understands this work. But even if you don't, or if there's somewhere where you're still getting lost, I'm sure that after you do this homework tomorrow and we go through these problems, things are going to start making more sense. Guys, I am Nonkulilego Matondo, and thank you guys so much for your patience and working with me through this class. And join me again tomorrow, and we'll be doing some more problems. It's all about physics, physical sciences, it's all about chemistry. And thank you. Goodbye.